In modern hardware manufacturing, survival isn't dictated by the millions you make in revenue. It's dictated by the pennies you save per part. When you are pressing tens of thousands of components, a margin of just a few euros completely decides whether a product lives or dies. To see exactly how engineering and procurement teams navigate this, we are going to look at a real-world case study, an existing hardware component facing severe margin compression from market forces. This graphic illustrates our current state, the IST price of 40.50 euros. Management's strict target is 35 euros, leaving a deficit of 5.50 euros. This is the value gap. The cost breakdown shows exactly where this money is absorbed. The standard corporate reflex here is to simply demand a 15% cost cut across the board. But brute force cost cutting almost always leads to a compromise on material quality, or it severely degrades the component's lifespan. There is a much more rigorous alternative. The European Standard for Value Management, DIN EN 12973, mathematically rejects the idea of compromising quality for price. Instead of looking at the physical part and asking how to make it cheaper, this standard shifts the optimization target entirely. It asks what the underlying function of the part is and whether that function is actually worth the price you are paying. The methodology to close this €5 gap without losing quality is already proven and documented, but putting it into practice introduces a massive operational bottleneck. The historic weakness of the DIN standard has never been its logic. It is the sheer velocity of data processing required to execute it. To do this properly, a human team has to manually aggregate CAD files, pull ERP data, calculate lifecycle costs, and synchronize cross-departmental specifications. This table outlines the reality of that manual process. Under a classic value analysis approach, gathering and analyzing all this data takes a team roughly 3 to 6 months to complete. We operate in an industry where procurement cycles and material prices are renegotiated every single quarter. A 6-month diagnostic is too slow, which is why this highly effective standard is frequently abandoned. We hear constant promises about artificial intelligence fixing supply chains, but AI is virtually useless for precision hardware optimization unless it is constrained by a rigid, engineered scaffold like the DIN standard. By deploying a specialized AI agent within this specific 9-step framework, we aren't replacing the methodology. We are using the AI purely as a compute accelerator to eliminate human latency. Look at the right side of the chart. When the AI takes over data aggregation and cost calculations, tasks that took weeks are executed in minutes. The net result is an 85% reduction in the time required to complete the analysis. By collapsing a 4-month diagnostic into a days-long sprint, the AI allows engineering teams to close that value gap faster than the market can react. The AI executes this through a 4-phase value engine. Phase 1 is preparation and strategic setup. Before human resources are deployed, the agent performs step 0, objective qualification, generating a fitness score of 88. It weighs economic impact, complexity, and data availability, pairing this with a risk priority number matrix for immediate visibility into implementation barriers. Once the project clears this gate, it moves into Phase 2, diagnosis. This is where the agent builds an unshakable informational baseline. The AI simultaneously pulls the technical specifications, CAD drawings, and manufacturing overhead to calculate a factual bottom-up should cost for the part. This chart visualizes the output of that diagnosis. The agent automatically runs a Pareto analysis, revealing that exactly 80% of the costs are isolated in just the first 2 subcomponents. This diagnostic phase completely eliminates emotional, departmental debates over where the problem lies. It replaces subjective opinions with a crystal-clear, data-backed cost structure. With the cost drivers isolated, the agent executes step 4, the FAST diagram, or Function Analysis System Technique. This is the absolute core of the DIN standard. To execute this, the AI forces engineers through a necessary psychological shift. You have to stop looking at the physical geometry of the part and start looking purely at its intent. Under the standard, every single function of the component must be abstracted into a strict grammatical pairing, 1 verb and 1 noun. Watch how this works. The AI dissolves the physical assembly into a logical tree. It categorizes everything into main functions, secondary functions, and undesired functions. Instead of a steel shaft, the system sees transfer power. Instead of a casing, it sees secure position. If you only analyze a physical metal bracket, your brain is constrained by path dependency. You will only ever design a slightly cheaper metal bracket. But by abstracting that bracket into the pure function of securing position, the AI opens the architectural design space to entirely new materials, cross-industry techniques, and radical solutions. The agent then takes these newly abstracted verb-noun functions and maps them directly against the exact financial costs we isolated in the Pareto toe. This scatter plot represents the value index, visualizing the mathematical relationship between functional utility and production cost. The focus immediately goes to the bottom right quadrant. These are overpriced functions, low utility features consuming a massive portion of the budget. This specific quadrant is the pivot point of the entire analysis. It mathematically isolates the exact functional gap where our return on investment is hiding. Only after this overpriced function has been isolated do we move to step 5, the creativity phase. Here, the AI agent shifts from an analytical tool into an innovation engine. It uses the isolated function to instantly generate dozens of potential concepts without any initial prejudice. To do this, the agent deploys several highly technical methodologies in parallel. It applies the theory of inventive problem solving, TRIZ, while simultaneously running design for assembly constraints. In seconds, the AI scans cross-industry benchmarks to find how other manufacturing sectors have solved this exact verb and noun problem. Now, this is exactly where standard generative AI usually fails. Left unchecked, a basic AI will hallucinate unmanufacturable, physically impossible designs that look good on paper but fail on the factory floor. Generating 30 new ideas is easy, but identifying the single concept that actually lowers the €40 price tag requires a ruthless, highly objective filter. That filter is found in steps 6 and 7, the Knutsford analysis or utility value analysis, where the agent rigorously scores every generated concept. The AI applies a multidimensional filter to the raw ideas, strictly separating viable, production-ready engineering from AI hallucinations. It evaluates each idea against a battery of uncompromising metrics: technical feasibility, estimated carbon footprint, and real-world time to market. This purely mathematical scoring mechanism strips out subjective bias and departmental pet projects. The output is a clear, mathematically superior choice. The agent ensures that only solutions possessing a fully validated payback period and a hard return on investment are permitted to advance. This filter acts as an organizational shield. It ensures that capital is only deployed against concepts that are mathematically guaranteed to close the value gap. We finally reach phase 4, realization. In step 8, the AI agent structures the surviving, validated data into a final executive summary. The output is a revision-proof, norm-compliant report that presents management with a clear, binary choice: implement or pilot the solution based on airtight data. But the agent's utility doesn't end at the presentation. In step 9, controlling, the AI transitions into the real-world production phase. Using a KPI cockpit, it actively monitors the implementation over a 12-month timeline. It continuously tracks the realized savings against the forecasted goals. Any deviations are instantly flagged and fed back into the AI agent as lessons learned, creating a compounding intelligence advantage for every future project. The DIN EN 12973 methodology is in the public domain. Anyone can use it. But by deploying AI agents to execute it, you compress months of complex analysis into days. This gives you the velocity to close critical value gaps and protect your margins before your competitors have even scheduled their first meeting.